Did you know your head ages faster than your feet? It sounds impossible, but it's true. Thanks to the strange nature of time itself, it's a tiny difference, but it reveals something profound. Time flows at different speeds depending on where you are. The higher you go, the faster time ticks, even if only by a fraction of a second. Gravity isn't just a force pulling things down, it's a deep connection between matter, space, and time. Every object with mass, from apples to planets, shapes the very fabric of the universe. This mind-bending reality was unlocked by Albert Einstein, who dared to question everything we thought we knew about the cosmos. His theory of general relativity didn't just tweak our understanding of gravity, it shattered the old picture, forcing us to see the universe in a completely new light. Before Einstein, space was a fixed stage, and time a universal clock. Unchanging, absolute, and the same for everyone, everywhere. But Einstein showed that space and time are woven together into a single, dynamic fabric, space-time. This fabric is alive, able to stretch, bend, and ripple. This fabric bends and warps in the presence of matter and energy, creating the effect we feel as gravity. Gravity, then, isn't a force pulling at a distance, as Newton imagined. Instead, it's the result of objects following the curves and contours of space-time itself. Planets orbit the sun not because they're being pulled, but because they're following the straightest possible path through this warped landscape, a path shaped by the sun's mass. This was a revolution in physics, replacing Newton's vision with a universe of elegant geometric beauty, where the very shape of reality is always in motion. But to understand how we got here, we need to look back at Newton, the giant whose ideas set the stage for Einstein's breakthrough and whose questions still echo today. Even Newton's laws, as powerful as they were, left mysteries unsolved, cracks that hinted at a deeper reality, waiting to be discovered. Newton saw the universe as a grand clockwork with space as a static grid and time as an absolute river. His law of gravity explained everything from falling apples to planetary orbits with stunning precision. For over 2 centuries, Newton's equations reigned supreme, even predicting Neptune's existence before it was seen. But Newton himself was troubled. How could gravity act instantly across empty space? He described what gravity did, but not how it worked. And then there was Mercury, a planet whose orbit wobbled in a way Newton's laws couldn't explain. The tiny precession of Mercury's orbit, just 43 arcseconds per century, was a stubborn anomaly. No amount of tweaking or hypothetical planets could fix it. Newton's symphony had a discordant note, a clue that a deeper truth was waiting to be discovered. The universe, it seemed, was more mysterious than even Newton imagined. The stage was set for a new vision. Enter Albert Einstein. After revolutionizing physics with special relativity, Einstein turned to gravity. His breakthrough came from a simple thought: a falling person feels weightless, just like an astronaut in orbit. Einstein realized gravity and acceleration are indistinguishable. This is the principle of equivalence. If gravity and acceleration are 2 sides of the same coin, maybe gravity isn't a force at all. Perhaps, he reasoned, massive objects change the geometry of space and time itself. When you stand on Earth, you feel weight because the ground accelerates you upward, preventing you from following your natural path through space-time. The falling person feels nothing. They're following a straight line through curved space-time. Einstein asked, what if gravity is not a force but a feature of space itself? This radical idea suggested the universe is a dynamic, pliable canvas shaped by the matter within it. The laws of physics, Einstein realized, are written in the language of geometry. To truly grasp Einstein's revolutionary vision, picture space-time as a vast, flexible sheet, a cosmic trampoline stretching endlessly across the universe. This isn't just a metaphor, but a way to visualize the invisible structure that underlies everything we know. In the absence of anything else, objects move in perfectly straight lines, gliding effortlessly through the emptiness of space, undisturbed and unbothered. But place a massive object on this sheet, imagine a heavy ball pressing down, and it creates a deep well, a visible curve in the fabric of space-time itself. Now, when smaller objects pass nearby, they follow curved paths. It's not because they're being pulled by some mysterious force, but because the very space they travel through is bent and warped. Planets, for example, orbit the sun not by being tugged by an invisible hand, but by following the straightest possible path, called a geodesic, through this warped space-time landscape. Gravity, then, is not a force in the traditional sense, but the manifestation of curved geometry. It's the shape of space and time guiding the motion of everything within it. Every object with mass, no matter how large or small, shapes space-time in its own way, and every object, in turn, moves according to the unique shape it encounters. Even light, which has no mass at all, must obey these curves. Its path bends as it passes near massive objects, following the geometry laid out by gravity. Einstein boldly predicted that starlight passing close to the sun would bend, a claim that could be tested and observed during a solar eclipse. This was a profound shift in thinking. Gravity is not a property of objects themselves, but a property of space-time, the very stage on which the universe unfolds. The universe, in Einstein's view, is a place where geometry rules and the shape of space determines the fate of everything within it. The next step was to put these predictions to the test. Would the universe reveal its secrets and confirm Einstein's radical new idea? Einstein's theory made bold predictions, and the first test was Mercury's orbit. When Einstein applied his equations, he found that the sun's warped space-time explained Mercury's mysterious wobble, exactly matching observations. The discord in Newton's symphony was resolved. Next came the bending of light. In 1919, during a solar eclipse, Arthur Eddington's team photographed stars near the sun. The starlight appeared shifted, bent by the sun's gravity, just as Einstein predicted. The news made headlines worldwide. Einstein became a celebrity overnight. The universe was not what we thought, it was stranger, more beautiful, and governed by geometry. General relativity had passed its first major tests. But the theory's implications went even further. It predicted phenomena that would challenge our understanding of reality itself. The adventure was just beginning. What else could this new vision reveal? General relativity's predictions were even stranger than bending light or Mercury's orbit. Einstein's theory didn't just rewrite the rules of gravity, it revealed a universe far more mysterious and dynamic than anyone had imagined. It showed that gravity affects time itself, clocks run slower in stronger gravity. This means that time, something we once thought absolute, is actually flexible, stretching and compressing depending on where you are in the universe. This isn't just theory. GPS satellites must account for time dilation or navigation would fail. Every time you use your phone to find your way, you're relying on Einstein's insights to keep you on course. Einstein's equations also predicted black holes, objects so dense not even light escapes. These cosmic enigmas warp space and time to their limits, creating regions where the known laws of physics break down. Once thought impossible, black holes are now observed at the centers of galaxies and in the dance of stars. Their presence shapes the evolution of entire galaxies, influencing the cosmos on a grand scale. Perhaps most elegant of all, Einstein predicted gravitational waves, ripples in space-time from massive objects in motion. These waves travel across the universe, carrying secrets from the most violent cosmic events. For a century, these waves were undetectable. Scientists waited, listening patiently for the faintest tremor in the fabric of reality. But in 2015, LIGO heard the faint chirp of two black holes colliding, a whisper from over 1 billion light-years away. It was a moment that changed our understanding of the universe forever. We had detected the sound of space-time itself ringing. For the first time, we could listen to the universe in a way never before possible. Einstein's vision was confirmed in ways he could never have imagined. His ideas, once considered radical, now form the foundation of modern astrophysics. The universe was speaking to us in a new language. Each discovery opened a new chapter in our cosmic story, inviting us to explore further. And we were finally learning to listen. With every new signal, we tune in more closely to the whispers of the cosmos. The cosmos had more secrets to share, and our journey to understand them had only just begun. Gravitational waves opened a new window on the universe. For the first time, we could listen to the vibrations of space-time itself. This new astronomy lets us study black hole mergers, neutron stars, and perhaps even the echoes of the Big Bang. Einstein's legacy is a universe more dynamic and interconnected than we ever imagined. His ideas form the foundation of modern cosmology. From the expansion of the universe to the GPS in your phone, it all began with a simple question, a happy thought about a falling man. Einstein taught us that the universe's deepest truths are often hidden in plain sight. We live in a universe where time stretches, space bends, and gravity is geometry. The journey of discovery continues with every new observation and every curious mind What else is out there, waiting to be